I want to talk a little bit about limits at infinity. Back in a pre-calc 1 class, um, you looked at lots of different functions, but in particular, you looked at these things called rational functions, polynomial divided by polynomial. And here's an example. One of the things we saw back in pre-calc 1 was that if you factor numerator and denominator, it tells you a lot about what's going on with the graph here. In particular, whenever the numerator is equal to 0, the function's got an x-intercept. Whenever the denominator is equal to 0, the function's got a vertical asymptote. Then, so let me plot those things. So for instance, at 1 and at -1 here, I've got x-intercept, so it's going to pass through those points there. I can find the y-intercept just by plugging a 0 in. It's easy enough, -1 over 1, so this is down at -1. Okay. It turns out that this denominator is never negative, so I don't have any vertical asymptotes. But you may recall that we also did something in a pre-calc 1 class where we sort of said, look what happens when x gets really big, right? When x gets really big, you got x squared minus 1 over x squared plus 1. So this would be like 1,000,000 minus 1 over 1,000,000 plus 1, when you plug x in. And it's like, what is that value equal? Personally, I look at it and say, well, if you're plugging in, x equals 1,000,000 and squaring it, the minus 1 is irrelevant. Likewise, the plus 1 is irrelevant. This looks like x squared over x squared. That looks like a 1 to me. And the answer is it's almost 1. And the bigger x is, the closer it gets to 1. And so there's what we call a horizontal asymptote here at x equals 1. Sorry, at y equals 1. Likewise, on the negative side, if x is headed out to negative infinity, then the graph is doing something like this. Okay. Now, from the point of view of calculus and our notation now, for this thing right here, I would say the limit as x goes to infinity of x squared minus 1 over x squared plus 1 is equal to 1. I have a horizontal asymptote, y equals 1. The function is getting arbitrarily close and staying arbitrarily close to that y value. Okay. The definition of the limit at infinity it's like epsilons and deltas. You're trying to get a handle of what do you mean by close. All right, well, first of all, I don't say x gets close to infinity, because you never get close to infinity. You just sort of tend to infinity. So I would say this. L is the limit as x tends to infinity of f of x if, right, what am I trying to say? I'm trying to say that the function is getting close to L. So that one I definitely have an idea of what I mean by close. I'm going to say plus or minus epsilon. So if for each epsilon bigger than 0, there exists, and now I'm trying to have something that says x is close to infinity. Well, x can't get close to infinity, but x can get big. So there exists a number n such that, all right, so if x is bigger than n, so this is saying x is close to infinity, whatever that means, right? X is big, then the function value will be close to L. So the difference between the function value and L will be less than whatever measurement you chose for closeness, right? If that's true for every epsilon bigger than 0, that there is such an n, such that x big means function value is close to L, then we have the limit. And we would say we have a horizontal asymptote at y equals L. Okay. Now, a similar thing happens if you're going to approach negative infinity, except that this would be x is less than n because you'd be going the other way, right? Calculating, there's some interesting things that happen. Let's look at this. The limit as x goes to infinity of about something like 3x squared minus 2x plus 7 over x squared minus 5x plus 1. Now, I'm going to show you a couple different ways to do it. Okay. Personally, I do this. X is headed to infinity. Okay, so pick a big number like 47, right? If I say 47 times 50 and I add 1, do I really care about the plus 1? If I say 47 times 2 and I add 7, does that, I mean, maybe at 47, so pick a bigger value of X. Pick like a million. So I've got 2 million, actually negative 2 million plus 7. Who cares about the plus 7? Who cares about the plus 1? For that matter, though, if I were to plug in a million, um, for X, a million squared would be a trillion. So this would be a trillion minus 5 million plus 1. Well, if I'm talking trillions here, I certainly don't care about the plus 1. And even the 5 million. I mean, a million squared is a trillion. That's a 1 with 12 zeros. Right? 5 times a million is a 1 with 6 zeros. When you're talking this much money, this is pocket change. This is just, I say money. I think in terms of money when I'm thinking big numbers because I have my dreams. Whatever. So my point is that the bigger X gets, the less significant the smaller powers of X are. And so I just look at this and say, cover up this stuff. This looks like a 3x squared over x squared. Well, I can handle 3x squared over x squared. That's just 3. So this limit is equal to 3. Now, I'm going to show you what the book does. And essentially what the book does is just justifies my saying it's only the big powers that mean anything. Okay, so here's the way you'll see it in almost every calculus textbook written. They're going to take this thing, 3x squared minus 2x plus 7 over x squared minus 5x plus 1. And I'm going to multiply by 1. I'm going to multiply by 1 in the form of, I'm going to pick actually the biggest power of x in the denominator. It happens to be the biggest power in the numerator as well. But I'm going to say 1 over x squared, top and bottom. The distributed property says this is going to be multiplied in every one of these and every one of these here, right, on the bottom. So this is the limit as x goes to infinity. So the 3x squared over x squared is just 3. The 2x over x squared is just 2 over x. Sorry, I got an extra plus sign in here. And the 7 over x squared is, well, 7 over x squared. On the bottom, the x squared divided by x squared is 1. The minus 5x divided by x squared, well, that's just 5 divided by x. And the 1 times 1 over x is, 1 over x squared is 1 over x squared. So, the thing is, in this stage, I think it's easier, I mean, for some people, it's easier to see. They look at this and they say, well, look at, as x is headed to infinity, what is 2 over x doing? Well, you get 2 divided by a bigger and bigger and bigger number. That's just going to 0. Likewise, 7 divided by this really big number is going to be really small. So that's going to 0. 5 divided by x, where x is getting really big, 5 divided by 10, 5 divided by 20, 5 divided by a million, 5 divided by a Google, right? I mean, that gets smaller and smaller and smaller as x gets bigger and bigger and bigger. This is headed to 0. This is headed to 0. Notice, all this stuff came from these terms where the power of x was small. The ones where the power of x is big left a 3 and a 1 here. They essentially just looked at those coefficients. And so what do we end up with? We've got 3 plus 0 on the top. We've got 1 plus 0 on the bottom. We got 3 divided by 1. The answer here is 3. Okay. So you'll see that time and again with when you're looking at the examples in the book. They would take this and always multiply top and bottom by 1 over whatever the biggest power of x is. Do it a couple times, but realize then what this is telling you is that you don't have to do it every time. You can just say, I'm only interested in the biggest power on the top and the biggest power on the bottom. Because when x is getting big, that's what's driving the situation. That's what's causing, that's what's showing me the behavior. Okay. We'll do some more examples in another video.